Welcome to this video on the electric field due to a ring of charge. And in this video and in a few more videos, we're going to take a look at figuring out what the electric field is due to different shapes. And some will use Gauss's law and some we won't. As we've been talking about Gauss's law and flux and all that sort of thing, I wanted to show you one not using Gauss's law so we can compare when it's a good idea to use Gauss's law and when it's not, or when you can't use Gauss's law. And we'll get through all of that. But remember, the main goal, the whole goal every time is how do you figure out the electric field when you have some sort of charge distribution that's not a point charge? And that's the goal. Okay, so whenever we're getting into all this hairy calculus and all sorts of expressions and trig and everything else, just remember that's what we're trying to do. So what we're going to do here is we're going to pick this point P over here, and the question is, what is the electric field at point P if it's some distance, we'll call this axis Z, away from the center of a charged ring? Okay, so we're going to call this a one-dimensional ring. So in other words, the thickness here is just to show the positive charge on it. And what we're going to do here is use some trig and some calculus and some algebra and everything else in between to help us figure out what the electric field would be at point E. Now what I'm going to do is I'm going to say the radius of this ring is uppercase R. And the way that I have this triangle drawn right now is I'm focusing on a little sliver right here of this ring of charge. Now, what we could think of, if you imagine this ring disappearing, and I have a point charge right here, a positive point charge, if I was trying to figure out the electric field right there, it would just be a point charge in space at r distance away from that point charge, and that would I'd be able to figure out the electric field, which we know at that point would be equal to 1 over 4 pi epsilon naught times q, which would be the q value over there, over r squared, with r being this value. Now we can't do that because the charge is not this one little discrete charge, but what we say is that the charge is continuous. That's an important term, continuous. So it's distributed continuously throughout this region. So we could say that a little region over here is affecting the electric field, and over here, and over here, and over here, and all over the entire ring. And so what we need to do here is figure out what the electric field, the net electric field, would be due to all these different regions. Now we're not going to use the concept of flux to do this because we are not using Gauss's law. And usually we will only use the idea of flux when we are using Gauss's law. So what I'm going to do here is I'm going to show you a method by which we can figure that out. And it's really just the vector addition method, but it's just using a few different other mathematical tools. So first things first, we have to draw the direction of the field at this point. Well, we know that the field, due to any of these tiny, tiny little charges all around here, would be pointing in a straight line away from that charge. So I might have one here, I might have one from this side pointing up, all around pointing in different directions. Regardless of that, because we picked the point right in the middle, I'm just going to isolate it here so I can draw this a little larger. What we're going to say is that the electric field vectors, due to each of the tiny little charges all the way around here, will have a horizontal, what we could call the parallel component, right? And then they'd have this vertical component like this. Well, these are all pointing in opposite directions, positive direction, negative direction, whatever you want to call it. And so basically what's going to happen is all of those horizontal components are going to cancel out, and all of the vertical components, right, are going to be pointing in the same direction. And so essentially what we're going to have is we're going to have a net electric field that's going at point P is going to be pointing straight up, and it's going to be the strength of all of those overlapping individual contributions of the charge all the way around the ring. So let that sink in. because that's the visual of what we're going to be trying to do here. All right. So at this point, what I need to do is then I need to figure out by angles what direction, trig direction or trig ratio that component of the electric field is. So what I'm going to do is I'm going to call this angle here theta, and I'm going to continue this line straight up like so, and just remember that that was the individual E vector, right? And I'm going to try to figure out what this component of the vector is. So opposite angle over here is also going to be theta, and then I know that I could say that this component here that's adjacent to the angle would be written as E cosine of theta. So E cosine of theta would give me that component. Now, it's the one that I've drawn right here, that's only due to this little point charge portion. And so I have to really call that dE, right? So it's a differential, a tiny, tiny little piece of the total charge or the total electric field. But all of the cosine components to that angle are the ones that I'm going to use to actually figure out the value. Okay, so I have this as the expression for just one region of the charge, but I don't have all of it yet. So what I'm going to do is I'm going to write an expression for just this one charge to start with, and then I can use some calculus to help us add up the entire charge. Now, when you have what we referred to before as a continuous distribution of charge, so whenever you have a continuous distribution of charge, what you want to do is you want to use what we talked about before as well, which is charge density. So we'd rather describe things in terms of charge density than just like total charge. And so what we're going to say here is that any tiny little piece of charge, which I'll call dq, is going to be equal to, and here we're dealing with a linear charge density, so I'll do lambda times ds, and ds is going to stand for a tiny little sliver, right? Tiny little arc length, right? Of which of course is exaggerated here in size, but is a tiny little arc length for that. So the dq is the contribution of the electric field due to just that tiny little ds value, with lambda being the linear charge density. Now I'm going to say that this is uniformly dense, so lambda is constant, but I'm still going to use that value. So what I could do is, if I was writing the electric field just due to that tiny little spot right there, I'm treating that as a point charge, right? Now I'm going to add up all these other ones eventually, but for right now, what I could write there is that dE, right? And we already have this equation from before for a point charge. I'll put it up here just for reference, and that's 1 over 4 pi epsilon naught times q over r squared. Now, because we're writing it as this differential of the electric field, I'm going to go ahead and write 1 over 4 pi epsilon naught, and then I'm going to put here, instead of q, I'm going to put dq, because I'm not doing this full total charge, but just that little piece, and I'm going to put it over r squared, because it still is the distance r away. Now what I'm going to do is I'm going to substitute this lambda ds in for dq. So I'll go ahead and rewrite this as 1 over 4 pi epsilon naught times lambda ds over r squared. Okay, at this point, we want to get some more constants in here, because constants are always good in terms of integrating, because if you are already kind of thinking about maybe the process that we're going to use, the process is that we're going to go and take this one piece and we're going to sum it up, right, using the integral. And so we want to make something here that has maybe more constants involved that we can use as a variation. So what I'm going to do is I'm going to write r squared as a constant, and r squared, right? If we think of that term right there, or r as a constant, I should say, r is going to come out to be the square root of z squared plus big R squared, because this is a right triangle. Okay, and that we're going to plug this expression in down here. So it's going to turn into 1 over 4 pi epsilon naught times lambda ds over z squared plus big R squared. And remember, the square root's gone because r was squared. All right, so we're at this point. Now, we recall the expression that this is right here is just dE, but it's not dE cosine theta. And that's the only contributing portion that won't cancel out, right? So this is just the electric field due to a small little piece of the charge, but it's its total electric field. Now I've got to multiply it by cosine theta. So what I want to do is come up with an expression for cosine theta, because if I remember, my ultimate goal is going to be to integrate this function, and if I have theta here, theta, it's going to add a whole nother variable that I have to integrate against, and this is ds, and that's theta, and so it's too many different things. And so what I want to do is I'm going to find an expression for the cosine of theta in terms of what I have here. Now cosine theta is equal to, if I look at this, it's going to be equal to z over r. I'll go ahead and write that down, z over r. And we already found an expression for r, right? So I'm going to go ahead and do this substitution. So it's z over, and that was z squared plus big R squared, and that's to the 1/2, or square root. Okay, so we're at this point, we're all good to go because we have an expression for cosine theta, and I have an expression for dE, and so I can just multiply those two together. So go ahead and do that right away here, and I'm going to put, let's do it over here, and I'll go ahead and write out what I'm doing. So let's go ahead and erase that, write this in. Okay, switch my color, and so I have 1 over 4 pi epsilon naught, and then I have times lambda ds over z squared plus big R squared. Now I have to multiply it by this times z over z squared plus big R squared to the 1/2. Okay, so when that's all said and done, the simplification for dE cosine theta is going to come out to be z lambda over 4 pi epsilon naught times z squared plus r squared to the 3/2. Okay, that's this, combining this down here. I've got my constants down there, and then I'm going to pull ds, which you could write up top here, but I'm going to put it over here on the side, just so that I can see, this is all the stuff that's being integrated, and it's with respect to the little segment of the circle. All right, so at this point, I'm ready to actually show the integration. So do a quick pit stop just to make sure that we understand what the heck we're doing again. Just a reminder, remember, we're just trying to figure out what the electric field is at this point, P over here. And we said that it's only the total amount of the electric field is going to come out to a cosine value of all of those added together, all pointing up. So I found an expression for the small amount of electric field made by this dq, and then I multiplied it by an expression for cosine theta, and now I'm going to do the integration. So essentially what's going to happen here is I'm going to say that if I take dE cosine theta and I integrate it, I should get my total electric field, which is what I'm looking for. And so that's going to mean that I have to integrate this side as well. So I'm going to pull out all the constants, and this is why we came up with all these alternate expressions. So let's take a look through here. Z is a constant, that's its fixed distance. Lambda is constant because I said it's uniformly dense. Obviously that's all a constant. Z again is a constant. Big R squared is a constant. And so pretty good to go here. So I'm going to go ahead and write this side over here. I'll write all my constants out front of my integral. So z squared plus big R squared to the 3/2. And then I'm going to integrate ds. And let's think about what direction I'm integrating. Well, I'm integrating from 0, which we could just call this point, all the way to 2 pi r, right? And 2 pi r is the circumference. And because I did a tiny little segment, that's what I'm working my way around. Okay, and so once the integration is done, and I don't have to worry about all this because it's just all a constant, what I should get is, and I'll do it, I'm not going to show the evaluating at the limits because this one's 0. So what I should come up with is z lambda times 2 pi r over 4 pi epsilon naught times z squared plus r squared to the 3/2. Okay, and now it can be simplified a little bit more. All right, so you can factor out some things if you want to. And so what we would have to do here, if we want to rewrite it, is we could put back, instead of using z lambda, we could put this as q times z. All right, because that would be the full amount of charge that's on the top. So I'll go ahead and write that in as well. So q times z, because this, remember, is lambda times ds, or lambda times the total length, right? And that is the same thing as the full charge. So go ahead and write this in. All right, and there we have a function that would describe the electric field for a charged ring. Now, if you make this, the last kind of thing that I want to look at here is if z goes really, really far, right? As z goes to infinity, think about it as this angle becomes really, 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 really small. And eventually, it's the same thing as just looking at it as a charge, as a point charge. So when, if you think about z going to infinity, right, r goes to basically to 0. And so then what I end up being left with is the electric field being 1 over 4 pi epsilon naught times q over z squared, because of the way that this would go as you went to infinity. So you'd almost treat it as if it were a point charge that you were really, really far away from. Okay, so you can see this process is not horrible, but it's very tedious. There's lots of steps, and if you aren't very comfortable with all these different expressions, it is kind of a lot. We're going to look at different ways to do this. What I would like for you to do is just make sure to familiarize yourself, write out the steps, write out how we started with trying to figure out E. We used the vector addition visually, and then we figured out all the expressions that we would need to use. And when we come back for the next video, we'll take a look at some other shapes, like if we had a disk where the entire thing was filled in and I had charge distributed throughout.